Ferrero. I'm a RAMS engineer, so reliability, etc. Industrial engineer, and also I'm a data scientist. So today I'm going to talk about diagnostics and prognostics with deep learning methods. So let's start. So first question here is, what are the typical maintenance problems which can be modeled by shallow or deep learning approaches, right? So machine learning approaches in general. So, well, first we have anomaly detection, which is just flagging anomalous behavior, right, in a component. And here we want the machine learning system to tell us or to notify us when this anomaly happens, so we can check the issue further, right? Then we have fault detection and identification, and here we want to know when there's a fault actually, right? And we want the system to tell us about this and also provide the classification so we know which maintenance actions can we perform, usually immediately. And then we have failure prediction and failure prediction. And this is actually is trying to answer the question, when will this item fail, or this component? It's going to fail in 30, in 31 days, in 32, right? Or alternatively, we could say, okay, a yes or no question. We could say, is this item going to fail in the next 30 days, for example? And then usually this can be enough, or not usually, but sometimes can be enough to plan maintenance according to if it's going to fail or not. Okay, so now I want to first talk a bit about deep learning methods in general, or what they can do, right? So deep learning, you can use it to analyze a very special type of data, like for example images, or sequential data, for example, like time series could be. And this could be used, for example, for visual inspection problems. So if you want to inspect for corrosion, for defects in the surface, for cracks, or also for sensor data, right, in the case of sequential data. So first I will talk about what deep learning can do in computer vision, because this is where it really excels. And so here we have classification and localization, or actually we could start with classification only. So classifying in each image which object is there. So for example, sheep in this case. Then we have localization, which is a regression task, and if the example is positive, or if it has the object we are interested in, then draw a bounding box around it. Then we have object detection, which is one step further to this, which we are interested not only in the class but also the instances of the class. So for this class, which are the instances, right? 1, 2, and 3. Then we can go even further to semantic cementation, and here the idea is that for each pixel, which class does this pixel belong to? That's the question. So there you can see these are pixels belong to road class, these to sheep, these to grass. And then you can do even further, instance segmentation. So you want to know which instance. So not only the class, but the instance, right? Okay. Then we have sequential data, like time series, could also be other types, but time series, for example, here the idea is to fit a curve to this time series, right? And for this, we can use recurrent neural networks, or one-dimensional convolutional neural networks, or a combination of both, right, as we will see later. Then we have general tabular data, which we could also use densely connected networks, but here it's usually not the best approach. I mean, you can do it and it can give a very high accuracy, but probably with shallow learning, like gradient boosted trees, you can still get very good results with less computational power. And also this, all these numbers doesn't seem to make any sense. So why bother, right? Now this is just a joke. It's important, of course. Well, then we have transfer learning. So transfer learning, it's not about cutting your head and giving your brain to your office colleague, like this picture suggests, but it's still about sharing knowledge between networks. So the image is still accurate. And what this means really, transfer learning is about you use a pre-trained model, right? Which you pre-train in a huge data set. So it's usually also a big model with many, many layers, like hundreds of layers. And then you can reuse it, this trained model, the pre-trained model, you can reuse it in other, in your particular data set for your particular application. So here it's a very, very simple diagram. If you see the left part, it's the base model, right, which is feature structure. And in the right side, you have the layers you put on top, your own layers, let's say it, or your own model that you put on top. And it's, well, in this case, it's a classified layer, but could be regression, could be many layers, of course. And the idea here is very, to say it very simple, is like, if you start down here, you can actually use your base model, your pre-trained model as is, so training a huge data set, and then just use it to your particular problem, freezing all the layers. So this means that you can train it with your trained data, with your particular data set, but you will just learn these layers here. Then you can do something in the middle, which is only freezing the first couple of layers, and let some layers in the base model to learn from your data, from your particular data set. And then you can go to the other extreme, which is, okay, just retrain the whole architecture again with your particular data set. So which one you choose, of course, it depends on your data. If you have very large data, you could consider the first one. Otherwise, it's probably not a very good idea. But also depends the similarity of your data, of your problem, to the one that was used to pre-train these models, right? So here it's an example of some base models like RESTnet, VGG, X16, 19, MobileNet. These are models with hundreds of layers, and they can be trained in huge data sets like Microsoft Cocoa, for example, which has 500,000 images or something, I think, or it has a lot. And yeah. Okay, so now that I gave this short introduction, so what's the state of the art in deep learning applications for maintenance problems? So in order to answer this question, I've been reading several papers in the last couple of weeks, and I have selected a few to show you a bit of what can deep learning do today. So first, this one is using deep learning and computer vision techniques to improve facility corrosion risk management systems by C.C. Ejimuda and C.M. Ejimuda, so all credits to them. And this was published in the Society of Petroleum Engineers journal. So here, so basically what they propose here is a deep learning model for detecting corrosion. So it's a detection problem. So what they do to train this model is they collected data from, they scraped data from the web, and they manually, they labeled each image, like according to one type of corrosion, galvanic, pitting, intergranular. And they also they draw the bounding boxes around the affected areas. And then they got only 36 images like this, which is very small data set, of course. So what they did after that is a technique called data augmentation. So basically they rotated the images, or created copies, rotated the images, maybe zoom in, zoom out, right? Change a bit the position. So they create synthetic examples doing this. So they finished with 336 examples for training. And then, so what they did here is a transfer learning approach. They used, as a base model, a RESTnet, pre-trained on the Cocoa dataset. And they put on top of that a faster RCNN for doing the classification and the regression, so the detection, the drawing the boxes, right? And they also tried with this mobile net, written on Coco plus the SDD, also for the same tasks. But in the end, they chose the first one because it gives better performance, with a mean average precision of 83% at an IOU level of 0.5. So IOU is how much the boxes they overlap, right? So here you can see the results. They have the boxes drawn manually on the test data, plus the ones drawn by the algorithm. Okay, so then I want to talk about CNN-based automatic coating inspection system by Lili Liu, Sti Tan, Si Qiang Kai, Si Jiang Yin, Yongda Chen from Singapore Polytechnic. So all credits to them. And this is actually, they do something very similar like in the previous paper, but there are a few differences that I want to show. So first one is they also use a pre-trained model, which is a G19, trained on ImageNet dataset. Then they put also a faster RCNN on top for the classification and detection. And then they also put on top a fully convolutional neural network for the segmentation tasks, so for classifying each pixel. But instead of scrapping data from the web, what they did was they used a drone, or they collected the data taken from a drone that takes pictures with a visual camera. So this drone inspects the offshore facilities, but it also not only uses a visual camera, but it also uses a infrared camera. So you see here this thermal camera. What it does is it can reveal and corrosion that is behind the surface or under the surface, right? So the idea with the thermal camera is that, you know, the area where the metal is clean, if you apply a heat source, the temperature goes up much faster than in a corroded area. So then this they emit different level of radiation, and you can measure that with thermal camera. And of course, you can do then segmentation, pixel segmentation out of this. So it's very interesting because they reveal not only superficial, but also behind the surface. Okay, so now I want to mention this very briefly, a review of deep learning in the style of material degradations by Will Nash, Tom Drummond, and Birbilis. This was published in nature.com. And I just want to mention one thing from here is they write this in section 5, which is, it is instructive that the areas where machine learning is making great strides are supported by freely available large data sets. Kitty for self-driving cars, ImageNet, and Microsoft Coco for object detection, and BRATS for brain tumors, to name but a few. Recognizing the social and economic cost of materials degradation and creation of these data sets to drive innovation in the field may be an appropriate undertaking for public institutions. So basically what they're saying here is that we need to have publicly large data sets in order to drive innovation for this particular problem, as it is the case in other domains, like, yeah. And the thing is that this requires some communal work or community work to attract researchers. Okay, then another paper also wrote by Nash and Birbilis last year, quantity bits quality from semantic cementation of corrosion images. Here what they do basically is they test, or they use a data set of 250 images, and they send it to high school students to do semantic segmentation. So it's not that trivial because you have to classify each pixel, right? And they did the same, but with a small data set with only 10 examples to some experts to label them. And but only 10 examples. So what they discovered afterwards was that when they trained fully convolutional neural networks for semantic segmentation with the large data set and the small data set, what it proves is that the large data set that was labeled by the high school students, so has cheap labels to see it somehow. It actually outperforms the other model because, of course, the other models tend to the model with the smaller data set, it tends to overfit very fast. But the one that is poorly labeled actually has some noise, of course, but still provides a good basis for the algorithm to learn. And you know the end of the story, yeah, it's written in the title anyway. Okay, and this last thing about corrosion, I promise. This is also a website created by Nash and Birbilis, and they make this website so you can upload your own image, and it can be corrosion can be detected in your image, and it's for free. So that's why I thought it was good to mention, because they also wrote in the website that the purpose of this website is to create a trained model for the automated detection of corrosion. This is an important endeavor, as presently no machine learning type model for corrosion detection is freely available. Please stop by this site often and tell all your friends about it. We are continuously looking for support, taking the quiz, blah, blah, blah. So, yeah, if you, this weekend, if it rains and you don't know what to do, you can check the website. Okay, so enough about this. Now, I want to talk about remaining useful life prediction of turbofan engine degradation using semi-supervised deep architecture. So here, this paper was written by André Listow-Ellefsen, Emil Björk-Lichau, Dilmar Astoy, Sergei Ushakov, Hujiang Zhang, and it was published in the Reliability Engineering and System Safety Journal. And basically, what they propose here is a model, semi-supervised architecture for predicting the remaining useful lifetime of this turbofan engine. So the data source they use is the CMAPS, Commercial Modular Aero Propulsion System Simulation by the NASA, which is a publicly available data set. And its data set is divided into 4 samples. So here you see the sensors that the data set contains. So it's temperature, pressure, fan speed, revolutions per minute. Then we have a training set and a test set. The training set lets all the engines run to failure. So you have the total lifetime for engine 1, 321, for engine 239, it was 255. So then with this, you can make a remaining useful lifetime label here. And in the test set, you have you don't have failure times, of course, but you have the age at the moment of the observation. So how long has this survived? And the idea is to predict the remaining useful lifetime for these engines. So here the architecture they use here is a semi-supervised architecture. And so here is the pre-training stage, which is unsupervised. And this, what it does, it gets the abstract features of data. It actually, what it does, it helps initializing the weights, so the parameters for the neural network to learn, instead of initialization randomly, or initializing them randomly. Then we have the LSTM's layers here. What they do is they learn the long-term dependencies. So what they are used for, recurrent neural network type. Then we have these feed neural network layers. So what they basically do is they map the features extracted from the previous layers to the output. And then in the output, you have the remaining useful lifetime, right, for a period. And then what is interesting about this is the results they got, because this paper is from this year, it's from March, and it's very interesting that if you see here, you have just focusing this one now. It's test error measured in terms of the root mean squared error versus the ratio of training levels. So if they start here, right? They train the model with all the labels they have, and they plot the test error. Then they say, okay, we remove some labels, so we are left with 90% or with 80%, and they train again and check. And they do this both for the semi-supervised architecture, which is the line in blue, and for the only supervised that they use as benchmark. So what you see here is that you remove some labels and still, or I mean, it's good. The semi-supervised architecture can learn this or can give a lower error compared to the just supervised architecture. And also in terms of the score function, so this is basically the same, but the test error is measured in terms of a scored function. And this score function, what it does, it actually penalizes more overestimations of remaining useful lifetimes rather than underestimations. So, because it's preferably to underestimate than overestimate, right? And then here you see actually that if you remove a lot of labels, so if you have only 30% of your initial training data labeled, you get significantly better performance with the semi-supervised architecture because of the pre-training unsupervised stage. And they got state-of-the-art results compared to other architectures. Then, I don't know how much time left I have, but this is another paper which is an improved bearing fault diagnostic methods using one-dimensional convolutional neural networks and LSTM by Honggu Pan, Xingji He, Sai Tang, Fanming Meng from Chongqing University in China. So this was published in Stringitz-Vestnik Journal of Mechanical Engineering. And what they do here is they combine actually convolutional neural network with the LSTM layers, and they achieved also very, very good results. So what they do here basically is that they measure the vibration or the amplitude of the vibration for a bearing right here, and this is the equipment they have: motor, torque transducer, and dynamometer. And the data set is actually from the Case Western Reserve University. So here you have the class labels. So you have 10 possible classes. The first one is normal condition, and the other ones are fault conditions for ball, inner race, outer race for different sizes. Basically, here you have how the vibration amplitude looks like for each health condition, right? And then here is the model they use. So they use convolutional neural networks, the pooling layer, which is part of the convolutional base, and the LSTM layer on top. So the output of this is used here as input, and then they got softmax layer for the classification. And they got accuracy rate of 100% for a test data set compared to other approaches which were slightly worse, but still very good. So they prove a concept. And so the takeaways here are, well, deep learning methods can be successfully implemented for diagnostics and prognostics, but what can be really a challenge is with limited label data or computational resources, because, well, of course, you know, because having failure data for machinery, it's not something that easy to get. Then we have also for visual inspection, you can use two-dimensional convolutional neural networks, and depending on which task you want to do, you can use different algorithms, different models. For sensor data, you can use one-dimensional convolutional neural networks or recurrent neural networks like LSTM, or a combination of both, as we just saw. And if you have limited data, you can try it with data augmentation techniques or upsampling techniques in general, of course, and downsampling, depends on your problem. Or also both upsampling and downsampling, depends on the problem. Then you can try with transfer learning approaches. You can try with semi-supervised architectures, and also dropout or batch normalizations, which they also applied in the papers that I mentioned, but I didn't mention, but they also applied dropout and batch normalization, so in some layers. And also the remaining useful lifetime, they used a genetic algorithm for hyperparametric optimization. So and finally, you can do what you have to do is experiment a lot with different architectures and hyperparameters because there is no universal solution for anything here. So you have to experiment a lot and see which architecture gives you the best results. And you need a lot of computational power if you want to train with large data sets, of course. So yeah, I hope you like it, and thank you very much.